Okay. Once we understand the basic idea of a rational exponent, we can also consider how this plays with our exponent properties. So there are a series of properties you learned when you first learned exponents, how it works when you're multiplying or dividing different bases, different powers of the same base. So the simplest example is if I have two powers of the same base being multiplied. Now you might remember as a rule, but I also want you to think of why this actually works. If you think of x squared times x to the fifth, well, that actually means x times x times x times x times x times x. So that is 7x's being multiplied. In other words, it's x to the 7th. So that justifies the idea that what we should do is add these exponents. What about division? The simple example, the simple explanation I frequently give is to think about where there are more of one of the variable. In this case, I can see that there will be the power of x on top is higher by 2. But the actual math of what you're doing here is saying, okay, I have 6 factors of x multiplied together in the numerator and 4 factors of x multiplied together in the denominator. If I divide these out, because all of those divide to 1, assuming x is not 0, then I'm left with simply x squared, which leads us to this rule that we subtract the exponents. Now that gets a little bit more precarious if we get a negative exponent, but we'll hold off on that for right now. What if I take a power of a power? Well, in this case, I can think about x to the 5th squared. What would that mean? That would mean x to the 5th times x to the 5th. And I could go ahead and expand this. I would have 5 x's multiplied with 5 more x's. Well, that's x to the 10th. So in this case, I know what I will do is multiply the exponents. And then there's this other issue of what if I take a power of some product? Well, what's going to happen here is each of these things will be raised to the p. In other words, I will take this exponent and apply it to each of the factors inside. So I will have x to the mp and y to the np. An example of why that works, again, if I think about 4x squared cubed, that means 4x squared times 4x squared times 4x squared. When I'm multiplying that, that's 4 times 4 times 4. That's 4 cubed. X squared times x squared times x squared, that would be x to the 6th. Which, of course, I can also simply write as 64, x to the 6th. So these are the rules that you came up with in Algebra 1. This is the justification. Now, when you do this with rational exponents, you really do kind of need to know it as a rule, because expanding it like this is not necessarily understandable. One of the other things you were talked about, there are 2 other exponent properties you needed to know, and that is if you raise something to the 0 power, it is always 1, unless you're taking a power of 0. 0 to the 0 is undefined. But the more important thing that we need to know right now is what does a negative exponent mean? And hopefully you recall that what a negative exponent means is a multiplicative inverse, or rather a reciprocal. So if I see x to the minus m, then that is effectively the same as 1 over x to the m. The base, I take the reciprocal of the base, and I change the sign of my exponent. Now, of course, if I write this, this would be 1 to the m, x to the m. Any power of 1 is just 1. So what that really is 1 over x to the m. Similarly, if I started a problem where I had a negative exponent in the denominator, I would resolve that by moving the x up top and again changing the sign of my exponent. So let's see how these properties work with rational exponents. So I'm going to start with the last property. What if I have a power of a product? So here I have 1/2. I will apply this to each factor. 9 to the 1/2 x to the 8th will become x to the 8 halves. Y to the 15th it becomes y to the 15 halves. And then I wish to simplify this if I possibly can. Again, I need to remember 1/2 power really means that I have a square root. So the square root of 9 is what this means. The square root of 9 is 3. X to the 8 halves, of course 8 halves is 4. And 15 halves is going to stay 15 halves. Can't simplify that. How about if I did this with a negative exponent? There's a couple ways you can do this. One way would be to take the reciprocal first and then apply the 1/3. Another way would be to apply this to each individual factor and then take reciprocals. Either way is valid. I will show you the second way. So if I do this, what do I get? Well, first off, those are all negative, which means I need to move them all down. I move them, and as I move them, I change the sign of my exponent. And then I want to look to simplify this as much as I possibly can. Apologies, my handwriting is not great. This says 27/3, not 17 halves. Well, these are all cube roots. So, the cube root of 216, you may recall, or you can break it down. 216 is actually 6 cubed. So I can go ahead and write that. I'll move this up. 27/3 is 9. 6/3 is 2. So then we get that. Now, I started with these first. They're arguably more important, in some ways more likely to come up, because this does represent essentially what you're doing with the radical. But we can really deal with any of the exponent properties with rational exponents. It's just not the prettiest thing in the world. Because what happens? If I had 10 to the 1/3 times 10 to the 6/5, if I'm multiplying two powers of the same base, then I know what should happen is that I should add the exponents. So the question then becomes, how do I add two fractions? And what I need is a common denominator. Well, 3 and 5, that's pretty easy. Those both go into 15. How do I convert to 15ths? Well, 3 times 5 is 15. I multiply 5 into the numerator and the denominator for the 1/3. 5 times 3 is 15. For the 6/5, I will multiply a 3 into the numerator and denominator. What does this give me? 1 times 5 is 5. 6 times 3 is 18. So I am left with 10 to the 23 15ths. Presumably I can leave it in this form. I wasn't asked to put it in radical form, but I could write that in a radical form as well and simplify it a bit. Since the numerator is greater than the denominator, there's one group of 15 in there if I did do that. I can also take a power of a power. 4 to the 3/4 raised to the 10/3. We know in this situation what we're supposed to do is multiply the exponents. How do I multiply two fractions then? Despite what some people might tell you or what you might think, you multiply two fractions straight across. 3 times 10 is 30. 4 times 3 is 12. 30 over 12, I can divide both of those by 6 and get 5 halves. So what I have is 4 to the 5 halves. Now be careful here. That's most of the work on this problem, but keeping with the idea that we should always make our answers as simple as possible, 4 to the 5 halves can actually be evaluated, because this means the square root of 4 raised to the 5th. What's the square root of 4? 2. What's 2 to the 5th? You can work it out, or you might remember because this has probably been seen a couple times. It's 32. Take a look at a few more examples. You'll notice also I've excluded an example where we have a division of 2 powers of the same base. It'd be the same idea. I'd have to subtract the fractions, but that's it. 7 to the 1/3, m to the 12th to the 9/4. So I know that in this case I would apply this exponent to each of these factors, to both of them. So I would have 7 to the 1/3 times 9/4 and m to the 12 times 9/4. So what I need to do is multiply those things. So when I'm multiplying 1/3 by 9/4, you could of course multiply this straight across and say 9/12 and then simplify that. That's one way you could do it. But another thing to be aware of is, since all of these factors are together in the numerator, and both of those factors are together in the denominator, I can actually simplify any factor in the numerator with any factor in the denominator. Namely, the 9 and the 3 can be simplified. And I can see that what I should actually have is 7 to the 3/4, which, had you multiplied straight across and gotten 9/12, 9 over 12 will simplify to 3/4. How about 12 times 9/4? Again, for a lot of you, probably makes sense. You're probably used to writing that over 1, although it's not something you 100% really need. And again, what could you do? You can multiply straight across and get 12 times 9 is 108 over 4. And 4 goes into 108 evenly. Or, as I said, the other way you could do this, 12 times 9 over 1 times 4. Simplify this, be left with a 3 and a 1. It's 27. So that's just some food for thought on how you could do this possibly more efficiently. Here's another random example I added. I have 2 cube root of x to the 5th, and I realized I'm going to use that number one more time. In this case, what I would do is apply this to each of the factors. So I would have 2 to the 5th and the cube root of x to the 5th. So there's a couple ways to answer this. If we want our answer in rational exponent form, then I know I need to write this as x to the 1/3 to the 5th. And I can say that this is 32 times x to the 5/3. Or, in radical form, what I would have is 32 times the cube root of x to the 5th, which there is a group of 3 there. This would be 32x times the cube root of x squared. So make sure you pay attention to the way a question asks you to give your answer, because there's often more than one way to answer a problem. Now you can play around with exponent properties and rational exponents all day, probably get better at fractions in the process. But one application which is worth noting, previously we said we couldn't do this problem because we have different indices, different indexes on those radicals. We had previously said in order to multiply 2 radicals I needed to have the same index, 2 square roots, 2 cube roots, 2 fourth roots, whatever. That's not entirely true. There's really a way around it regardless of what I'm trying to multiply. I might not get a particularly meaningful or pretty answer, but in this case, these are both radicals including a 3. The radicand in both cases is 3. So what I have is 3 to the 1/4 times 3 to the 1/2. And I know in this case what I would do is add 1/4 and 1/2. Well, 1/2, I can convert that to fourths by multiplying by 2 over 2. And what I have is 1/4 plus 2/4. So this is the same as 3 to the 3/4, or the 4th root of 3 cubed, or rather the 4th root of 27. So that would be the simplest radical form. Just some food for thought. As always, hopefully that has helped. Let me know if you need more.